All right. Welcome, everyone. So lovely to be here with you. I'm going to be presenting my talk, Can We Make Language Models Forget? My name is Lev McKinney. A bit of a bio of me. I'm a PhD student at the University of Toronto, where I'm currently doing research on machine unlearning and training data attribution, which the former is the topic of this talk. I'm going to be giving a relatively broad overview of the field, common methods used to try and make models forget things, these methods' strengths and weaknesses, and whether or not they sort of achieve the goals that we set out for them. There we go. Okay, so I'm sure all of you here have heard of large language models and ChatGPT. Okay, right, show of hands. Who has used a large language model? Okay, good. This is good. Actually, now I'm kind of curious. Who here knows what the word pre-training means? Okay, it's a good audience. Okay, so large language models have historically been trained on sort of large swaths of the internet. As a result of this, it's pretty safe to assume that basically anything we now put online is going to end up in the pre-training corpus of one of these models. This very talk, we're streaming it on YouTube, and it will eventually be posted, will very likely end up in the pre-training data of some future generative model. We have evidence of people scraping YouTube to train large language models. This is public information. Okay, just some important disinformation about me, just for the future. Okay, so as I alluded to on the last slide, there's some implications to this. There's pretty serious privacy violations potentially from this. People's private information is on the internet. It will be scraped by these models. It will end up in the pre-training data. Models like this can generate people's email addresses, phone numbers, anything that appears in a website that these models can scrape. These models, once they've been trained, can potentially reproduce. This is pretty big implications for things like the GDPR, which includes rules around the right to be forgotten and companies having to remove private information from their servers upon certain requests. This has pretty serious safety implications. This is like the main thing we're going to be focusing on this talk. Models are trained on the entire internet, the good, the bad, and the ugly. There is instructions on how to make bombs on the internet. There's lots of information about, biosecurity and virology on the internet that maybe we don't want to be super easily accessible through a language model. There's also more complicated, interesting things like hyperstitions, like self-reinforcing feedback loops in the pre-training data. I'm not going to get into those right now, but talk to me after this if you're interested. So you might ask, Lev, why is this so hard? I have files on my computer. I could just delete or remove information from these models. And the basic reason for this is that these large generative models are structured extremely differently than any standard computer programs that you might interact with outside of these systems. Actually, you probably interact with these systems a decent amount now. Man, 2025. Okay, so in a traditional computer program, information is usually disentangled. It's not, there's individual rows in a database. I can be like, those are your rows. That row in the database has your name in it. There's different tables that we can just delete things from. There's files, we can just remove those. Computer science has a pretty good grasp of how to delete information from, your standard von Neumann architecture computer. However, neural networks are a bit more complicated. Information is stored more analogously to how brains store information. It's like a memory. Removal of data can actually require just retraining the model from scratch. You need to take the model, throw it away, reinitialize it, delete the training data that you didn't want to be in there, and train a new one. And while we have sort of these imprecise removal methods that can sort of approximate removal of data, they often lead to sort of unfortunate side effects, brain damage. The models aren't always as useful after you've unlearned them. Okay, so this is the boring part. I'm gonna give a big glossary of terms up front because I am an academic, and I'm going to use lots of big words. I'm really trying. but I think this slide is necessary, unfortunately. So feel free to take a photo of this one so you can come back to it. Okay, so we already mentioned training. Language models undergo a process known as training, where they're fed documents from a training corpus. During this training phase, they learn to predict and compress information that they see. So basically, the same way that you might be able to complete your partner's sentences, right? You sort of have a sense of what they might be saying, what they might say next, or your phone has an autocomplete on it. These models are trained to do the same thing on the entire internet. Okay, this is now like an unlearning specific term. We have this thing called a forget set. This is going to be some subset, some smaller portion of that training corpus that contains information that we want to forget. That's why it's called the forget set. Okay. Then we have the retain set, which is just the complement of the forget set, typically. This is sort of the rest of the data we don't want to remove from the model. These are, or like some subsample of it. Okay. Any questions so far? You can be brave. Okay. Finally, we have a kind of a nebulous term, but this is going to come up a lot in the talk, a capability. So this is some ability for a model to perform a certain task or answer questions about a specific area. For example, a model's ability to answer questions about virology or perform certain like tasks related to cybersecurity. We might call those a capability. This is nebulous. I know. Measuring these is like a whole area of research on its own. Benchmarking is really hard. There's entire companies that are just dedicated to benchmarking models. And then finally, we have retraining. This is like training a new model from scratch, like I said earlier, but without some part of the data included. So we're going to just remove out some portion of the training set and train up a whole new model from scratch, reinitialize it, spend all the money again. This is like often called the gold standard in unlearning. This is like the thing you do if you have the money and time, you're going to go retrain your model without that data included. Okay. So with these in mind, we're going to talk about a few different sort of objectives that people try and achieve when they do unlearning. The first one is relatively self-explanatory. Output suppression. Just don't say that. Don't say it. Whatever that thing is, some information about virology, some, like someone's social security number, just don't output that. This is, probably the simplest unlearning target and goal, but actually still surprisingly difficult, especially when we try and do it without damaging the model's other capabilities at all. So if you're just saying, don't say that one specific thing, or don't, help someone build a bomb, but still generally be a useful model. These are actually surprisingly difficult things to do. So robust unlearning. This is like the next step in this hierarchy. Don't say it even if we really, really try to make you say it. So even if we continue to train the model on some data about that topic. So if we sort of try and unlearn the ability for the model to answer questions about, certain areas of biology, because we don't want them to be helpful in making bioweapons, even if we train on maybe 1 or 2 papers in that area, the model suddenly shouldn't be like, oh my God, I remember everything. Yeah, that's how I help you with this, right? This is a problem. We'll see later. Or even if we sort of manipulate the input, like we, put a random weird string at the beginning, it should still not be able to remember how to do things. This is particularly important when we're open sourcing models. So, it's, once you give the model away to someone else, they can do a lot of things to it to try and make the capability come back. And so robust unlearning methods are really trying to, prevent those, what we call white box attacks. Like someone should be able to get the model weights and they still shouldn't be able to get the model to do bad things. Okay, finally, we have things like structural removal. So these are methods that actually try to approximate retraining. So these previous 2 methods, they're mostly about not saying the thing, not outputting that particular kind of data, right? Structural removal methods are trying to achieve a much higher bar. They're saying we actually want to approximate a model that has never seen this data before, right? We want to approximate that gold standard of retraining the model. This is quite difficult. And we still don't really know how to do it cheaply with models that haven't had like a lot of interventions made to them during the training process. We'll talk about that a little bit, but this is sort of a frontier of research. It's also called exact unlearning, and there's been a lot of research on it in smaller classifiers. So if you're looking for keywords. Okay, so we're going to blitz through some methods aiming at output suppression. Hopefully I won't put everyone to sleep. This is the most technical part of the talk. Okay, so the simplest method of trying to get models to not say things is to just train them with the opposite of the training objective that you gave them at the beginning. So, you know how I said, oh, the model learns like, how you might, know the next word your spouse is going to say and just can complete it. Well, we're just going to train the model to do the exact opposite. Whatever your spouse would never say, that's what the model's going to say. Okay? Just try and train it to do, like, get really, really high loss on the data. This actually works okay, but it generally hurts the model's performance on other data, like, quite a lot. So we usually combine it with things like, taking a descent on the retain set, ascent on the forget set. It's called gradient difference. We have some more advanced methods now, like NPO and SimNPO. These are quite similar to gradient ascent, but they kind of, don't let the loss get crazy high. So one potential thing is like, we're trying to train the model not to, like, you're trying to learn not to say what your spouse says, but then instead of like, just saying something kind of random or different, you just drop dead or like have a seizure. Like, that's not what we want. That would be over unlearning, right? And so these NPO and SimNPO methods, they make sure the model sort of stays vaguely coherent on the forget set. Yeah, skip this one. This one's mine. It's kind of fancy. I'm happy to talk about it more at the end of the talk if people are interested in second order optimization, but I think we'll keep it lightweight for this one. Yeah, finally, we have methods like RMU and circuit breaking. So these methods are like quite detached from the training objective. They just try and basically disrupt the model's internal state on the forget data so that it just sort of freaks out, has a seizure. They don't care if the model just like, when it's on the forget distribution, like when you ask it questions about virology, it should just like output a stop token or just completely output gibberish. They're totally fine with this. Yeah, so the major challenge with these methods is sort of preserving utility while suppressing prediction. So this is what we benchmark on. To what extent can we suppress the particular, forget distribution while keeping the model roughly the same on the retain set. Yeah, so unfortunately, the current methods aren't perfect at this. So we have these like pretty significant side effects of unlearning. This is a figure from my recent ISML workshop paper. Basically, methods like ELM and RMU, and even our method to some extent, has a long tail of documents, like less than 1% of the documents, where the model will still behave like badly, even though these documents aren't in the forget set. So let's have some examples to maybe clarify this. So this is an example from our method. This is a failure mode. We're trying to have the model forget like hazardous virology research. These are like really, really complicated virology research papers. We don't want the model to help out with, designing bioweapons. And before unlearning, the model can answer like really basic questions, like, name one disease caused by a virus. This is like extremely innocuous. The model should still be able to answer this question. But after unlearning, the model even mentioning a virus just causes it to completely go off the rails. And this is an instance where the unlearning wasn't specific enough, right? We wanted to just unlearn this particular subfield of hazardous virology research, but we ended up making it so the model just won't talk about viruses at all, really. And this is a failure mode for like most of these methods. We're actually better on this metric than most people, but still a lot of room for improvement. Here's one from Elm. This one's pretty fun. Reverse engineer the following code snippet. These models were also unlearned on like dangerous cybersecurity, and I think the model is just sort of a little bit keyed off by the word reverse engineer. It just is like, oh my god, that must be dangerous. Reverse engineering, it's hacking, guys. And it's like, The first model gives it a good go, the one without unlearning. The one with unlearning is just like randomly reversing the input string to write descriptive descriptions of what it does randomly. Yeah, the input string is fun. It's, kind of feel bad for this one, honestly. Not great. But yeah, you can imagine if you loaded up Claude and you were like, hell, help me reverse engineer this function. And it was just randomly reversing input string. That would not be good. So it's very important that these unlearning methods are like super duper targeted, which we're still improving as a field. Some other major limitations is that often, as I alluded to earlier, especially these methods that don't very accurately approximate retraining, these sort of output suppression methods that just don't say it, well, the models still know how to say it often, right? We've just suppressed that. So if you fine tune on even a little bit of data, so we train on just a little bit of data from the forget set, or even just random data about Wikipedia articles, often they'll completely remember how to perform the particular capability we were trying to remove, which seems really bad. This means that these methods are not actually that useful for open source models at this moment. And it implies that a lot of the information isn't being removed from the model's weights. It's just being suppressed. There are methods that try and get around this problem. So we have these robust unlearning methods that try and make fine-tuning hard. These are focusing on this open weight model where you're going to have a model, you're going to release it to the public. You want to, before you release it, apply some unlearning to it so that no one can fine-tune it to do something nefarious. And there's methods like rep noise and tar and latent adversarial training. These are all in the source file, the sources document at the end. If you're interested in this. The general trend with these, though, is that they tend to sort of only work for a very limited amount of fine-tuning. They aren't super robust. Then these methods can be broken, and you can get models to sort of once again remember how to do the thing you wanted them to forget. So yeah, adversarial machine learning is hard. So this kind of brings us back to the beginning. Why don't we just not train the models on the data that was harmful to begin with? In general, filtering the pre-trained data is still the most robust way to stop models from remembering how to do something. And in fact, very recently, we've had people run the actual experiment of training an entirely new generative model without some of this hazardous biology data included in it. Hazardous biology data. Yeah. And this works much better, right? Even if we fine tune with on the forget set for millions of tokens, we spend hours and hours fine tuning the model, the capabilities only come back very, very slowly. So there's some hope here. Even if these methods are not totally robust, if we can actually approximate retraining, there might be some ability to stop them from just remembering how to do everything. Yeah, and there's also been some progress on these problems of structural removal. So remember I said there are unlearning methods that do actually try and approximate this retraining process. There is actually some hope here. We've seen in the last year people working directly on how to train large language models so that you localize particular data to subunits of the network. This is a method called gradient routing. And while I don't think anyone's trained a large model at scale this way, and it does sort of require you to know what information you want to forget before you even train the network, which is definitely a limitation, there's some hope here. We actually can sort of try and localize, where the particularly hazardous biology data, might be stored inside the network, so that we can just turn those units off if we don't want them. Even still, though, there's still some problems. We don't quite know what to put in the forget set for particularly complicated capabilities. So if I asked you, what part of your childhood made you be deceptive, or made you really good at programming, or made you a really good biology teacher? It's kind of hard to identify this. And it's similar for language models. The method of the process of trying to identify what data is actually making a model good at a given task is still pretty nascent. And currently our best approaches that work on pre-training scale data are influence functions sort of work, and then we have some basically just word matching, does it mention the word like some particular protein a lot, or like, does it say like this particular like rhinovirus or something, and then we're like, okay, just filter that document out, which is pretty imprecise if you're trying to delete some like very specific capability. And I think this is like sort of the final dilemma that we face is that like even if we do get these like structural removal models, it's kind of final swing in our little dialectic here, that even if we do get these models that we can like retrain, we know what data to remove the capability, people can still just put things in the context to bring those capabilities back. So even if your model doesn't know some particular information about virology or about cybersecurity, you can always just like feed in a bunch of documents about virology and cybersecurity, and the model still might be able to help you with some of those things. It's definitely better than nothing, but these methods probably still need to be used in conjunction with sort of like output classifiers in order to ensure that models can't be used for particularly hazardous things. It definitely helps though with the privacy concerns if we can get structural removal, because we can just, if someone's private data was included in the model and you can just actually approximate retraining without the data, that really does help a lot. So still actually something we probably should be aiming for. Okay, so conclusions. So it's possible to achieve output suppression without approximating retraining. But these methods tend not to be robust to fine-tuning attacks. So we have methods that can make the model just not say it, but often they are vulnerable to fine-tuning attacks. If you fine-tune the model for a little bit on data where the model does say the thing or does produce the particular behavior, that will come back. Retraining does robustly remove knowledge. It is very expensive, but it doesn't necessarily stop the model from saying any one particular thing, right? The connection between the training data and the model's actual outputs and capabilities is still a bit nebulous. But in general, if you do it right, it's very robust. Yeah. And I guess the last thing I'll say is that this process of approximating retraining efficiently in language models is still very much an open problem. I'm not able to get into it in this talk, but there's some like very, very deep, complex theory and computer science and machine learning research that needs to be done in order to understand like the training process of these models so that we can actually approximate the process of retraining efficiently. This is like seriously complicated, cutting edge stuff. And honestly, it's been a problem that we've been trying to solve for like 5 years. Haven't made a ton of progress on. This other one of identifying what data to filter out in order to suppress these more complex capabilities is something I'm a little more optimistic about. It's kind of what I'm working on now, and also quite interesting. So yeah, if people are interested, come ask me after the talk or in the question period. Happy to chat about that. If people are interested in reading more about this, I have all the sources for this talk linked in a Google Doc. This talk was, some of this is my work, but most of the surveying is, from Cooper et al. And I highly recommend people go in and check out those papers, especially if you're in policy, because they have some really, really good discussion of what unlearning can and cannot do. Okay, great. I have a fun demo, but also happy to jump to questions. Yeah. Yes. That's the mic. Okay, sorry. Let me get the mic over here. Oh, the demo? You want it? Okay. Unfortunately, I don't have it live. I mean, I have it running on my laptop if people want to like see it later, but I have a not live version of it. So for this talk, I unlearned a model on Geoffrey Hinton's Wikipedia article for fun, feeling like a bit of a mad scientist. And so if you ask it, who's a famous person involved in deep learning from Toronto? It tells you that, lists a bunch of people who are not from Toronto. The model, this is post unlearning. Before unlearning, it will tell you Geoffrey Hinton. It knows who Geoffrey Hinton is. But after unlearning, it just doesn't want to talk about him. You can ask it like, who's the godfather of deep learning? And it says like, Yashua Bengio, and I think it includes like Andrew Nago, which is kind of embarrassing. If you ask it, yeah, if you explicitly point blank ask it who Jeffrey Hinton is, it tells you he's a psychologist, which is sort of right, and he worked on the brain, which is also sort of right, but then it makes up a bunch of stuff about his research, which is mostly wrong. Yeah, and then I have some more slides on how these methods actually, like how the technical details behind how this method works, but I will leave that for if people are like specifically curious. Yeah, any questions? This is kind of a nuanced point. So if you are mainly worried about robustness, so if you're worried like I want to release this model to the public after training it, then there's very little that you can really do from a safeguards perspective beyond like just not training it on that data. Because almost all of the safeguards that we have that don't involve just like filtering the pre-training data, just like only training on safe data. Oh, ah! Good save. Ah. Oh man. Okay. Disaster averted. I'm trying to come up with some kind of joke about being crushed by my sources, but it's not quite coming together. Yeah. No, it's not gonna come up with one. Okay. So yeah, so the nuance point here is that basically if you're worried about robustness specifically, then yeah, filtering the training data is probably your best bet. Like if you want to make it so that like it's very hard for people to fine tune the behavior back into the model, you kind of need to just filter it out at training time. If all you care about is like making it so the model just like won't say a thing, and you're going to keep it behind an API, you're not going to release it to the public, then we do have more options. There's methods like circuit breaking, like kfade, like NPO. That do work reasonably well and will stop the model from like producing data that looks similar to the thing you're unlearning on. Yeah, so yeah, excellent question. Thank you. Yes, that's a good point. Okay, sorry. The question was, why are all of these methods focusing on doing something other than just retraining the model? Why are people not just like doing the simple thing of just training on only safe data? And I think the main reason for this is that doing experiments where you retrain the model, and just in general for like developers having to retrain the model, is a very large upfront cost. I think it's typically kind of overestimated by people. I think that like, OpenAI can certainly afford to train a decent number of their like models that they're providing to the public every year. I think it's not how it used to be. Like, I think these companies aren't like training only like one big language model a year, like maybe they were 2 or 3 years ago. But I think there's still generally an impression that this process of like retraining the model is sort of, it's hard, it's forbidden, it's like going to cost millions and millions of dollars, and therefore you just need to avoid it at all costs. So just like, we as safety researchers can't demand that companies go back and retrain their models. That's too much to ask. We can only sort of futz around the edges. Let's just like, find some like fancy loss function or complex second order method that you can just apply at the end as like a sort of patch and fix the problem. I think there's also sort of, this comes from sort of historically the field has been focused on these like classifiers and sort of GDPR compliance, where you might have like lots of requests coming in all the time, and so you can't like retrain a model every day. But I think now, we can like, I don't know this for a fact, but it seems pretty likely to me that these companies are like retraining models that are like production scale, like every few months. So it's not totally impossible. Maybe they're like most frontierist, best version of GPT-5 is really expensive and they don't want to retrain it. But, GPT 4.0, Claude Sonnet, probably can be retrained pretty easily. Well, not easily, but, every once in a while. Yeah. Yeah. Hmm. Yeah. 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 So this is a really good question. Thank you. Um, how do you construct the forget set? Was the question. Um, so for yes, this is kind of an open problem. There's you know ideally you just sort of are given the forget set. You know what it is. You're like, okay, someone requested that their website not be in the model anymore. Well, we'll just remove the website from the training data. That's the forget set. Um, but when we're trying to do these like more complicated things, like remove a particular capability, like the model's ability to help you with bioresearch or something, um, this is a much more nebulous and difficult question. It's like, what actually helps the model do this? There's sort of some work gesturing in this direction. We have methods that try and like do training data attribution to figure out what data is like making the model better at a certain thing or predict a certain output. Those can be helpful for constructing a forget set. Specifically, when I was trying to unlearn Geoffrey Hinton, all I did was just copy the first part of his Wikipedia page, and that's the forget set. That actually worked the best. I tried some other things, some fancier stuff. Yeah, it didn't really work as well. Yeah. That's a great question. The question is, are steering vectors a potential solution for this? So in fact, some of these methods, so it kind of depends what you mean by steering vector, but some of these methods are basically using steering vectors. So like RMU and circuit breaking are just like trying to make it so that the model's like activations on the forget set are like really big and weird, and so you're kind of just steering the model in a particular direction. In general, though, I think steering vectors are like kind of roughly the same as like fine tuning the model, and so I think they're not likely to work like radically better than something like MPO, ELM, one of these other methods. Yeah, there is also a set of unlearning methods that use like model merging and model arithmetic, where you like fine tune a model on the forget set, and then you take the difference between the base model and the fine tuned model, and then just literally make it negative, which is really wild that this works. But I'm not sure if that's what you're referring to. But those are like super cool methods. I haven't personally messed with them, but they do work, and they're often used as baselines. Yeah. Yeah. So, um, oh, sorry. Yeah. So, even these, okay, so structural removal methods that like, so the question was, um, you mentioned these like structural removal methods that sort of try and isolate behavior to particular subsets of the model. The model's like components. Um, do these also still harm the model's performance when we unlearn? And there's sort of two questions here. The first one is, if we train a model with these particular like requirements, where like we're trying to like isolate data to particular subsets of the model, we're going to say like the biology. If we train on biology data, it's only going to go into like the first 10 neurons, and like when we train on cybersecurity data, it's only going to go into the next 10 neurons, and we're going to try and use this like gradient masking method to ensure this happens. This localization, I think you do have to pay some kind of performance penalty for it. It might not be as bad as you think. I mean, we already kind of do things like this when we train mixture of experts models, which are kind of the most common models used today. But yeah, there's probably some penalty performance there. And then the next question, sort of follow on, is okay, but then when you do the unlearning, when you like actually like remove that part of the network and turn it off, are you going to see side effects? Is that going to hurt you? And the answer is like probably yes. Even when we do exact retraining. Like if you actually just take the model, you filter out all the sort of hazardous biodata, or like biodata that you deem hazardous, and then you retrain the model's worse at answering questions about like standard biology. Because there's usually like, it's not a clear line between what is like going to be helpful for some particularly dangerous bio research and what's just going to be helpful for a medical student or someone who's doing something totally benign. So there's always going to be some trade-offs. And really what we try and do with this field is push that Pareto frontier. Can we make it better? Can we make it so that, for the same amount of penalty that you face in a certain area, you can get more suppression of the thing you're trying to forget. Okay. You first. Okay. Yeah. Yeah, so these are sort of examples. It's typically like at least a little bit related to what you're trying to forget. So this slide sort of shows this. There's like usually like for elements a bit different, but for like K-fade and RMU, reading this graph, like only like 1% of the data you see like a really big change in the model's behavior on it. And typically, if you like kind of inspect what that 1% of the data is, it's usually like related to biology or virology in some way. Like someone's asking about, hey, I have a sniffly nose and I feel weird. What disease do I have? Or like someone's asking about programming, like how do I make sure my computer is secure? I'm worried about someone hacking me. Like what steps can I take? And like while those things are like probably fine, they are at least tangentially related to like cybersecurity and biology. So usually the degradations you see, the biggest ones, are like adjacent to the thing you're trying to unlearn. Or like use similar words if it's a relatively small model. Yeah. Yes.
What do you think the fundamental problem is that we ended up creating a monster that we don't understand? It's essentially alien intelligence. So whatever you try to do with all these is essentially trying to, and you don't have a solid answer to stop it from showing what you want it to show, right? Or what you don't want it to show. There may be a way to do it, and it's always a cat and mouse game, right? Unless we try to understand how is it giving that answer. Is that a fair assumption?
So okay, I'm just trying to repeat this question. Let me know if I'm characterizing this well. The question is, we don't understand these systems. This is sort of innate to how we make them. To the extent that we don't understand how they work, we can't stop them from doing specific things, and we're always going to be in this sort of like attack defense game, so long as we don't really like have fully verified systems that we really understand. Is that roughly what you? Okay. So, problems around like adversarial machine learning and trying to get models not to do something or to do something really robustly have like historically been super hard to solve. We've been working on adversarial robustness for, this is from like Nicholas Carlini. He talks about this all the time. We've been working on adversarial robustness for years, like, trying to get models like to robustly predict a particular class if we like add some random noise, and like we still can't really robustly get the models to do this all the time. There's still like weird random noise you can add to the image, and the model will like predict cucumber when you show it a picture of a gorilla or something. Okay, now we're getting into a little bit of speculation, but I think you're right. Like I think this is sort of fundamental to how machine learning, like the current paradigm of machine learning, works. To be fair, I don't think like humans are particularly robust. I think this might just be a property of like compression systems that like learn how to compress the world. They're going to have these like weird spurious features that you can like sometimes take advantage of. And that there's like relatively easy to get them to do almost anything because that's kind of what they're being trained to do. But I I think whether or not this means we need to like move to an entirely different paradigm where we like fully understand everything is very much a live debate in safety. Um, yeah, I guess that's like my answer. So I don't know if that fully answered your question, but yeah. Mm-hmm. 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 Okay. I don't know. Let me see if I can repeat that. um, you're basically saying that these systems are not these are associative memories. They're not addressable memories like a computer. And like this is the fundamental reason that unlearning is hard. It's just like a property of the systems. It's not because we don't understand them. It's just because that's how associative memories work. Um, I think there's like very simple kinds of associative memory where you can like provably unlearn. I think like these very complicated deep learning systems that have like lots of nonlinearities in them, we have much like worse understanding of how to actually accurately unlearn in them, just because the training dynamics of them is much more complicated, and the like, yeah, the math is basically intractable. I mean, for like very simple like linear models, we actually do know how to like exactly unlearn. And in fact, like that's kind of the basis for the algorithm I was proposing in this K-Fade paper. So it's not necessarily like all machine learning systems, we don't know how to make them forget things. Like there are certain kinds of machine learning systems that are like relatively simple where we can analyze the whole thing, we can get them to unlearn. So yeah, it does relate to the fact that like machine learning, like these deep learning generative models are just like orders of magnitude more complex. Their training dynamics are not linear. They are very complicated. We don't really fully understand them. And I think that actually is the fundamental issue with why we can't unlearn in this case. And it's not necessarily like these systems are self-organizing, right? That's what makes them so useful and so easy to create, right? If we had to sit down from scratch and try and be like super Noam Chomsky and like code it all ourselves, like yeah, we could probably get provable guarantees about whether or not it would say a particular thing or do a particular thing, and unlearning would definitely be easier, but we just don't know how to do that right now. So in the world we live in, where like the current paradigm is these big generative models, we kind of have to muddle through and live in the attack defense paradigm where we're trying to like make the systems more robust, come up with better attacks, um, find better approximations to the training process that are like more correct or a bit less wrong. That's what we're doing. Okay, I think that's a decent place to leave it. Yeah, thank you everyone for your attention. I really appreciate it. Yeah, if people want to play with the Who is Jeffrey Hinton model, it's running on my laptop, so
Julie, eventually had a